He's a specialist of various sorts of geometry, and he made several major contributions to the field of dynamical systems. And he was awarded the Hubbard Prize in 1987. And I will give a little quote from Bill Thurston. I have long held a great admiration and appreciation for John Hubbard and his passionate engagement with mathematics. Hubbard has inspired me and others. So I am among the others, and I will also be among the others in 1 hour from now. Let's welcome Professor Hubbard.
Well, thank you very much. I would like to thank the KAIST Department of Mathematics for inviting me and giving me a chance to give this lecture, and particularly Dan Zaffron. So I'm going to talk to you today about the Mandelbrot set. If you wonder, what was the dream of people like Newton, Lagrange, Poincaré, Birkhoff, Kolmogorov, what would those people really have wanted to do? Well, what they really would have wanted to do is to understand the parameter space for dynamical systems. Newton really wondered what initial positions of the planets would lead to stable motions and which ones would be unstable. Lagrange studied this problem a whole lot more. Poincaré spent his whole career thinking about such things. Kolmogorov spent much of his career talking about such things. The problem is that it is immensely difficult, and there is essentially no parametrized family of dynamical systems that we understand at all, with one exception. Well, there are the linear ones. We understand those pretty well. But the nonlinear ones, there is one exception, and that is this case of quadratic differentials, quadratic polynomials. Maps. After all, if you're going to study the next case after linear functions, what could be more natural than to study quadratic polynomials? Now, what does it mean to study them as dynamical systems? It means that we're going to look at some initial z0, and then to set z1 is equal to p sub c of z0, z2 is equal to p sub c of zn, of z1, and so forth. Another way of saying this is that zn is p sub c iterated n times of z0. This little circle n means iterated n times. It means in this case, we do just about understand the parameter space for quadratic polynomials. But I think you will agree by the end of the lecture that it is a whole lot more complicated than you would offhand have expected. Now, what are we really asking? We are asking the question, how do such sequences behave, both as a function of z0 and as a function of c? Well, in general, there is nothing really simple to say about how a sequence will behave. You don't know what question to ask. You don't know what a reasonable description is. But in the case of polynomials, they don't have to be quadratic. There is a form of behavior that you can clearly see, which is for any C, if Z0 is sufficiently large, Zn will tend to infinity. So one behavior, which obviously is possible, is that the sequence will go to infinity. That's for polynomials. For other maps, you may not be able to even figure out any reasonable behavior, but for polynomials there is always that one. So this leads to a very natural description. K sub C is equal to the set of Z such that P sub C iterated n times of Z does not tend to infinity as n tends to infinity. And this is a definition that you're not allowed to forget for this lecture. Nothing else. Maybe I'll write it on this side also so that it stays there. And in some sense, understanding such sets K sub C is what understanding iterations of quadratic polynomials means. K sub C is always a compact subset of C. And understanding what kinds of compact subset it can be is a major task. So let me show you what some of these look like. Oh, maybe I should say ahead of time that there are two values of C for which Kc can be understood. If C equals 0, then Kc is the unit disk. And that is something which I expect everybody to be able to know. And if C equals minus 2, K sub C is equal to minus 2, 2, the closed real segment minus 2, 2. And maybe you won't find that quite so easy to check, but it's true. For all other values of C, K sub C is some complicated fractal thing. So, before very long, I'm going to explain what this picture is. But let me give you an idea as to what the scale is in any case. You see on the blackboard the C plane. This is 0. This is minus 2. This is minus 1. This is I. That's the scale. So you're looking at the C-plane. 0 is here. This is 1/4. This is minus 2. This is minus I. And when I go click someplace, click, 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 I'm choosing a value of C, so I'm choosing a particular KC. And when I go click, you're going to see KC come up. So, 0. I said it was the closed unit disk. Pretty close. I didn't hit on 0 exactly. Someplace inside here still looks rather like the closed unit disk. Over here. Just think, you start iterating z squared minus 1. If you start inside the black region, you're going to stay bounded forever. If you start outside the black region, you're going to go off to infinity. And in fact, I can show you those iterations. But if I start outside, you can see what those iterations do. And in fact, you can see that wherever you start in the black region, that's in that k sub minus 1, you are attracted to an attracting cycle of period 2. You are attracted to the pair of points, this point and this point, where this one maps to here and this one maps to there. 0 maps to minus 1. 0 squared minus 1 is minus 1. Minus squared minus 1 is 1 minus 1 is 0 again. Here's a rather famous one. You're being attracted to a cycle of period 3. Well, here you're being attracted to a cycle of what period? Hello? What is the period of this cycle?
7.
It's 7, and more or less obviously it's actually a 3/7 cycle. But there's pictures that are really different that you could get, such as this one. In this case, K sub C is a Cantor set. You may not believe me that this is really a Cantor set, but what is a Cantor set? It's a compact subset of the plane. Well, it's a compact set in any case, which has the property that it's totally disconnected. The biggest connected subsets are points. But on the other hand, it's perfect. No point is ever isolated. So let's see whether that's what we see. So let's make a blow up, say here. It certainly falls apart into several pieces. Let's make a further blow up here. Certainly falls apart into several pieces. Let's make a blow up here. Falls apart into several pieces. A typical Cantor set. A pretty Cantor set, but a Cantor set for all that. And in fact, there is a theorem which asserts either 0 is in KC, which occurs if and only if KC is connected, or 0 is not in KC, which occurs if and only if K sub C is a Cantor set. This is probably more or less fatu. So it's a theorem which is now about 100 years old. Under these circumstances, it is very natural to consider the set of C's for which K sub C is connected. M, the Mandelbrot set, is equal to the set of C such that K sub C is connected. Which is also equal to the set of C such that the sequence 0, C, C squared plus C, C squared plus C, the whole thing squared plus C, and so forth, is bounded. This is what makes it interesting, and that is what makes it computable. In the old days, computing pictures of the Mandelbrot set might take all day. The old days aren't all that old either. We're talking about 1980 or so. Nowadays, it is often used as a screensaver on computers, and as a result, probably many people have seen pictures, many pictures of the Mandelbrot set without having any idea of what they were looking at. Okay, so this is the Mandelbrot set, and it's the structure of this set that I'm going to be talking about. Understanding the Mandelbrot set is essentially the same question as understanding quadratic polynomials as dynamical systems, understanding the parameter space of polynomials as dynamical systems. In fact, that's the Mandelbrot set. The black is the Mandelbrot set, and the colored locus is where it is not. And if you look at the definition, well, if you look at this side of it, it's easy to see what the colors represent. If 0 is not in KC, then it has to escape to infinity under iteration. And you can ask a question like, what is the first n, such that the nth term of this sequence is in absolute value bigger than 100 or something like that. It's a perfectly good question, and that gives you the colors on the outside. Another question that you might really wonder is, why is 0 so important? Supposing I'd written 1 there, or 5, or or some random number. Why 0? Well, Fatou didn't just prove this. He proved a theorem which is absolutely wonderful from the point of view of one-dimensional dynamics. What he claimed is, if you want to understand a one-dimensional dynamical system, the first thing to understand is what happens to the critical points. What happens to the places where the derivative is 0? Well, you'll notice that for the polynomial z squared plus c, the only place where the derivative is 0 is the point 0. The derivative is 2z, and 2z equals 0 means z equals 0. So, what makes this 0 special is that it is the unique critical point of the quadratic polynomial as written like that. And if you wanted to write your quadratic polynomials some other way, it should always be at the critical point that you start iterating. That's Fatou's rule. Always start at the critical points. Also, that explains why there's no theorem like this for cubic polynomials. Because cubic polynomials have two critical points. And then you have to worry whether one critical point escapes, or the other one, or both, or neither. And all of these are... what happens is that if no critical point escapes, then K sub c is connected. And if all critical points escape, then K is a polynomial, is a Cantor set. And then there are all kinds of intermediate possibilities, and life becomes much more complicated. It is still absolutely not true that people understand the parameter space for cubic polynomials. Tells you something about how much progress there has been, that even cubic polynomials are still very mysterious. But quadratic polynomials are okay. So you see, if I click anywhere in the black, I get something connected. And if I click anywhere in the color, I get a Cantor set. If you don't believe this is a Cantor set, well, you pull the same sort of thing as I was pulling before. You can see it's obviously a Cantor set. Now, one thing that I would like to tell you is that the Mandelbrot set is complicated. It doesn't look too bad at this resolution, but let's go and look a little carefully someplace. Oh, that isn't what I want to do. What you saw me do there is I'm always essentially computing this sequence and asking, does it escape? Does it get big? But of course, I'm not going to write a billion terms of this sequence. It would take much too long, and I would blow up the computer. I have to stop somewhere. But there's a question about knowing how soon I stop. And I just changed that. I changed it. It was 200 before. Now it takes. I decide that it's not going to escape if it takes 2,000 moves at least. This program will do it at almost the same speed if I go up to 20,000. The other one has to do with the colors. You have to decide how to interpret time of escape into colors, and if you don't use a logarithmic scale for that, you'll start seeing, well, you're seeing 2,000 colors. Well, it's hard to put 2,000 colors, so you have to spread them out in an intelligent way. Okay, so there's that blow up. And now let's perhaps go and blow up in here. And now let's go and blow up, oh, I don't know. Every place is just as bad as every other. Or just as beautiful. Take your pick. Okay, now you see a blow up of the Mandelbrot set. So the object of today's lecture is to give a name to every dot. I want to understand that set in the sense that this is Jimmy and that's Robert. I know the name of every single point. It's in that sense, it's that level of precision that I am looking for. And I'm going to give it to you. But I hope, I'll do a few more if you're not convinced, but I hope that this sequence of pictures was enough to convince you that this was not going to be obvious. That it is not obvious that this picture, well, I don't know, it's highly organized. Obviously it's highly organized. So I mean this, one can talk about chaos, but that does not look chaotic. It just looks complicated.
So from the second from the top, below that corner, there's also Mandelbrot set.
Well, I'd have to go and I think that if you go down there, you'll do various things.
Like region, this Mandelbrot set.
This region here? Oh, that region. Okay. So let's just erase this. And you do see a little copy of the Mandelbrot set here with a whole decoration around it. But you'll find there are lots and lots of them. They're all over the place. For instance, inside here, hey, you find another one. And now if you go over and look inside here, well, I don't see it yet, but let's go and look inside a little bit further. Ha! See it there? But this Mandelbrot set has its own pattern of decorations around it, which is different from the pattern of decorations that there was before. And some people talk about things being self-similar. The Mandelbrot set is as far from self-similar as one can possibly get. And I'm going to tell you the precise sense that that means. I will talk to you in just a second. It is not self-similar in the sense that every point contains its address in every neighborhood of itself and in the topology of every neighborhood of itself. So you choose some point, chunk, and I allow you to look only in a circle of radius 1/billionth around that point. And then I don't allow you to measure anything. I just allow you to measure how many points, how many pieces come together at various points within there. From that data, you can figure out where you are. Now surely that is the strongest possible meaning of not self-similar. That every point contains its address in every neighborhood of itself. And in the topology of an arbitrarily small neighborhood. Now, there was a gentleman up there who wanted to ask a question.
So this black set I see here, this is a rotated
It's
copy of the first one you showed me. Or
so all that I know how to prove is that it is a quasi-conformal copy of the Mandelbrot set. I do not know how to prove that it is, for instance, a differentiable copy. And I think it is not true. In fact, come to think of it, I know it is not true.
okay.
Because there are spirals, and from a spiral there's a complex number attached to a logarithmic spiral. And the spirals of this Mandelbrot set are not the same as those of other copies of the Mandelbrot set, so it cannot be a differentiable. The question of knowing how nearly differentiable and just how quasi-conformal it is a big subject of research in its own right. Okay, so I made a pretty fancy claim. I claimed I was going to give a name to every dot. And how is this going to happen? Well, interestingly enough, it's going to happen via complex analysis. Complex analysis, the Riemann mapping theorem, and such things are the fundamental tools for understanding this object. It is beautifully adapted to complex analysis. So the first theorem in this direction is the theorem is connected. Now, this has the consequence, by the Riemann mapping theorem, that there exists a map phi sub m from C minus m to C minus the closed unit disk. There exists a conformal isomorphism. That is what the Riemann mapping says. Riemann mapping theorem says. Who agrees that that is what the Riemann mapping theorem says?
It's a complement.
Excuse me?
You map the Mandelbrot set to the unit disk. Isn't that the Riemann?
Well, I can't map the Mandelbrot set to the unit disk. The Mandelbrot set has some wild topological structure, but it's a connected subset of C, compact connected subset of C. So the outside is simply connected. The outside is simply connected if you add in the point at infinity. And then you can map the point at infinity to the point at infinity. And this theorem is true. But the Mandelbrot set, hey, you're not going to map the Mandelbrot set to the unit disk. That's just not going to work. But interestingly enough, you don't prove that M is connected and then write the say that the Riemann mapping theorem gives you that. It goes exactly the opposite way. You construct the Riemann mapping theorem and then you discover that M is connected. So, yes?
M path connected?
We do not know. That is the one open question about this. The question of whether M is locally connected, which is equivalent to its being, well, it isn't quite, it's a stronger statement than its being path connected, is not solved. It is, there have been 2 Fields medals for partial results. There have been 2 Fields medals for partial results, but that is one thing that is not known. But the analogous statement for cubic polynomials is known to be false. So, and I don't know, you look at something like this and you ask, is it locally connected? Well, I don't know. I look at that and it really makes me wonder. But I have looked at millions of pictures and yes, the answer is going to be yes, it is path connected, but we just don't know how to prove it. I don't know how to prove it. Okay, so the name of the game is to construct phi sub m. Now, let me, I'll tell you what, I'm just going to stop this program altogether and start it up again. This is the Mandelbrot set again, but represented a little differently. Now let me go over to this and that and who will agree that I have here drawn the conformal map, that I have drawn this map? I claim that there is an obvious map from the colored region here to the colored region here. You see it maps that to that, and then this to this, and that to that, and so forth. I have drawn a map that goes from C minus m to C minus d bar. In fact, there's something really extraordinary here, which is, I computed this live, you know. This isn't some canned picture. I computed the conformal map of the complement of the Mandelbrot set with all of its complications much faster than I would be able to draw the conformal map for the complement of a square. From the point of view of complex analysis, the Mandelbrot set is rather simpler than a square. And you might really wonder, why on earth does it work? How was this thing computed? Okay, so, but let's see what part of the audience agrees that I have here a drawing of such a map, that I've established that I could pick a point here and figure out what the corresponding point in the outside of the disk is. Shall I pick somebody in the audience to come and tell me where this point goes? Is there a volunteer to go and tell me where this point goes? You look like a volunteer to me.
I think it's pretty, if I think about it for a while, then it looks like we can construct a map, like we wrap this Mandelbrot set by an open disk, and then sort of make this one identify using conformal map, and then we go inside a little bit further by drawing some kind of simple path around this one and construct one.
Okay.
And go in and construct the sequence of
So, let's decide that this line corresponds to this line, which seems likely on the basis. Then the place which I was choosing, this one, is inside that line. So I should be inside this line. And then I need to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I'm in this band. 1, 2, 3, 4, 5, 6, 7. Well, no, I'm in this band. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That point there corresponds to this point here. Now, how many people agree that I have drawn such a map? I still don't have any agreement.
Not sure what happens when we get closer and closer.
What?
Not sure what's going to happen when we get
Oh, okay, sure. Well, then let me say a little bit more. What you were really reading off, there are, if there is such a conformal map, then you have straight lines going to infinity, radial lines here, mapped to some place. And I claim that what you are seeing here is reading out the angles of those radii in base 2. This picture, if you looked at it bigger, and I can make it bigger, let's make it bigger. So, on this side, very far away, you have two lines. I actually didn't go far enough away to see two lines. And then at one level further, you have 4 lines. And you do see the one with 4 lines. So here are the numbers which start with point O, and here are the numbers which start with point 1. I'm counting my angles in turns, and I'm writing them in base 2. Then here are the ones that are point 00, point 01, point 10, and point 11. Then you go one step further. And here are the ones which are point 000, point 001, point 010, point 011, point 100, point 101, point 110, point 111, and so forth. So, drawing a line through here, or perhaps through here, tells you the digits in base 2 of the radius of the angle of the external ray that you're looking at. Now let's try the same thing over here. So there obviously is a ray which lands there, coming in like this. What do you think that angle might be? Well, we can try to read it off. Well, where's that pointer there? So we want to end up down there. So start here. Red, green, red, 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 red, green. You can see that that number is the number point 001, 001, 001, 001. i.e. it is the number 0.001 that repeats in base 2. Now, how good is your arithmetic in base 2? What angle is that? Huh? What is 0.001 that repeats in base 2? Well, as it turns out, that number is 1/7. It's true. Okay, so eventually, when I get to the point where I tell you I'm going to give every a name to every point of that picture, what I'm going to do is that the name that I'm really going to give is that the name is going to be the angle of the external ray that lands at that point. That's the name. And then I'm going to claim that that name reflects the dynamics of the polynomial that's at the end of the ray. That's what's really going to happen. Shall I say that again a second time? The name of this point on the boundary of the Mandelbrot set is 1/7. That's Mr. 1/7. It's also, as it turns out, Mr. 2/7, because there are two ways of getting to it. You could come this way, or you could come that way. And that way, as it turns out, is 2/7. Now, what does 7 have to do with that point? Well, 7 is 2 to the 3rd minus 1. And this 3 is, by elementary number theory, the same 3 as the length of the repeating segment. But as it turns out, it is also the period of the attracting cycle that exists throughout this region. If you go to this region, you will see that there is an attracting cycle of period 3, and it is not by chance that in this region there is a cycle with period 3, and that the angles of the rays that cut off that region also repeat with period 3. I assume this talk ends at 5:30? Yes. Okay, well, I guess I really have to tell you something about where the complex analysis is coming from. There is a first statement which says, so I'm afraid that I'm going to speed up a bit. If you have a polynomial of the p sub c of z equals z squared plus c, it is always true there exists phi sub c from c near infinity to c near infinity such that if you do here p sub c and here just z gives z squared, this diagram commutes. Near infinity, there exists a unique local coordinate in which your polynomial, whatever it is written as z gives z squared. And in fact, what are you seeing here? What does this drawing represent? What is it? It is the local coordinate. It is the coordinate in which your map is z gives z squared. Now this works just fine. It's defined on the whole complement of k sub c when you're in the Mandelbrot set. But when you aren't, it doesn't. If you aren't, if I choose a point like, say, this, then you can see that this local coordinate in which it looks like z gives z squared will work up to the time when you hit this point, and then it doesn't work anymore. So this is the first proposition 1. And proposition 2 says 0 is in the boundary of the domain of phi sub c, and c is inside it. Zero, where's my cursor? There, where's my cursor? 0 is in the domain, boundary of the domain. Maybe I could make a better picture here. Maybe I'll try to pick this value here. Is that better? Maybe it is. You can see that phi sub c can be defined down to here, but not inside here, where things start breaking up. So, phi sub c can be defined down to the value 0, but not beyond. However, c, which is phi sub c of 0, C do you see that point right there? There is 0. There is C. P sub c of 0. C is in the domain of phi sub c. As a result of this, you can define if C is not in the Mandelbrot set, you can define phi sub m of C is equal to phi sub c of C. There's this marvelously referential thing, self-referential thing, where this C is C viewed as the parameters, as in the parameter space, and this C is C viewed as an element of the dynamical plane. So the theorem really says phi sub m is an isomorphism of C minus m to C minus the closed unit disk. And this is relatively easy. Once you've thought of doing this, the hardest part of all of this is proving that proposition 2. Well, proposition 1 isn't trivial either. Proposition 1 isn't trivial, proposition 2 isn't trivial. And this, well, it's more or less obviously analytic because phi sub c is analytic as a function of both variables. And then it's a restriction to a line of an analytic function of two variables. And it's analytic, and you have to show that it has that it's proper of degree 1. So you have to say that if you get really close to the Mandelbrot set, then the critical point escapes very slowly so that you're very close to the boundary of the disk. And then it has a degree. And actually, it isn't so obvious that the degree is 1, but it's true because you can figure out the asymptotics at infinity and show that, in fact, infinity is its only inverse image. So it's proper, it's analytic, proper of degree 1. And that's shows that it's an isomorphism. Well, once you've done that, you've more or less carried out my task of trying to give a name to every point of the Mandelbrot set. And because of this formula, you can see that that name reflects the dynamics of the polynomial. So one example, for instance, is to consider the polynomial z squared plus I. That's an interesting polynomial. 0, the critical point, maps to I, maps to I squared plus I, which is minus 1 plus I, maps to minus 1 plus I squared plus I, of which I don't know how your complex arithmetic is going, but it turns out to be minus I, which maps back. As it turns out, is at the end of the ray at angle 1,6, and 1,6 is equal to 0.001, which repeats. So the dynamics after one jump, the points repeat. The digits after one jump, the digits repeat. In that sense, the name of the polynomial, the name 1/6 of the polynomial I, reflects the dynamics of the polynomial, that it is pre-periodic with a pre-period of length 1 and a period of length 2. Well, it is 5:30 on the dot, and I think I will stop there.